by Mr. Alain Legault. He is the VP, I'm going to take this off, sorry. He's the VP of Marketing at Hardent, where he's responsible for spearheading the product definition and development of the company's semiconductor IP portfolio. Please help me welcome Alain.
Thank you, Sai. Hi, everybody. How is everybody today? Good? All right. So my name is Alain Legault. I'm coming from Montreal in Canada. And it's nice to be in Taiwan this week because it's starting to get kind of cold in Canada. We're going to have some snow this week, believe it or not. So I'm here to talk to you about VESA DSC. DSC stands for Display Stream Compression. It's about video compression. First, I'm going to tell you what is VESA DSC. Then I'll take a few examples in consumer electronic and what you can do with DSC. And finally, I will cover a little bit about how could you use DSC, how to go around using it in your next semiconductor design. So first of all, why do we need DSC? Well, there's many examples in the industry where typically you have a processor that transfer high-definition video data to a display module technology. It could be a mobile with the MIPI DSI link. It could be a computer GPU card with a DisplayPort cable over a monitor, or maybe a car with an application processor transferring to a display module inside the car. And the problem that we've had in the last few years is that the growth of the bandwidth requirement for the display technology have gone much faster than the increase in speed of serial transport technologies. And I mapped out the DSI link over the years, and basically it went up by 3x over 5 years, where the actual display technology went up by 10x over the same amount of time. And this gap over there is creating a problem. There's not so many ways to get around this problem. One would be to increase the number of lanes to be able to maintain the data transfer bandwidth. But of course, that comes to the expense of additional pin, additional power requirement, extra logic. Or you could use compression. But nobody wants to degrade picture quality. So that's what VESA worked on starting in 2013. And the Video Electronics Standard Association was able to come up with a very clever set of algorithm called DSC that essentially allows you to do lossless picture quality. So the VESA algorithm, in a nutshell, is a constant bit rate encoder. That means that you have a fixed data rate, very precise over your transport link. And with a set of clever algorithms that are based on DPCM, there is a midpoint predictor, a block predictor, MMMAP, and an ICH algorithm. There are many of them that work in parallel to give you best picture quality no matter what is your content. So many algorithm works well with, say, natural images, but they don't do so well with text and graphic. VESA DSC is extremely good at a lot of them. The other aspect to VESA DSC is we want it to be low cost. So only a single line of video is required inside the static RAM to do the encoding, and that gives you an ultra-low latency. We're talking about less than 1 microsecond for a 4K video. So that's in a nutshell what it is. This compression technology at 3x allows you, for example, in the case of, say, 4K video at 60 frames per second, we're looking at 16 gig of data per second. Well, with 3x, it allows you to reduce the number of lanes in MIPI by substantially. So, for example, with DeFi 1.5, version 1.1, you would have a really hard time to do a 4K product without DSC. With 3x compression, it will only require 4 lanes. So this is extremely effective. So essentially, you end up putting a DSC encoder in your processor and a decoder in your display technology, and you're in business. When we started, only a few companies were involved in setting up the standard. We're talking about people like Qualcomm, Hardent, and Broadcom, and a few others. But nowadays, the video task group, the DSC task group became a lot more significant because of the wide interest in the industry. We now have two versions of the specification. We have version 1.1 originally that was based on RGB color space with 444 chroma sampling in 8, 10, and 12 bits, which is essentially what was required for the mobile industry. More recently, we came up with a version 1.2 that extends the capability by adding YCBCR support in 422 and 420, as well as a deeper color chroma sample up to 16-bit per component. This capability increase number of application and bring things, for example, like digital TV application. And we're going to come back to this because, of course, the idea is to bring this transport, this compression technology to various transport. The very first standard that supported DSC in terms of transport has been the MIPI DSI 1.2 version. And so there was early on a liaison effort between the VESA and the MIPI Alliance. And subsequently, VESA brought the DSC technology and the newer version of DisplayPort, DisplayPort 1.4, as well as the embedded DisplayPort technology. Much more recently, actually, HDMI, which is just about to release their 2.1 specification, have added the support of DSC on this version. Which obviously bring the digital television application. There are also other transport technology. One is called HD-based, which is used in Pro AV and automotive application that also specify DSC as a native compression standard. So there's many technology that are standardizing about the use of DSC. But why adopt DSC? Well, I mean, one of them is the benefit of the extra compression, but there are others. So I'll illustrate this by using this diagram that shows essentially the subset of a mobile phone. So you have the application processor that transfer video picture over MIPI DSI to the display driver IC that has a frame buffer on it. So when you add DSC encoder, you can eliminate some of the MIPI lane because you don't have as much of a bandwidth, but you also can remove static DRAM, some of your frame buffer. You can actually shrink it by 2/3. So the benefits as you have less power requirement, smaller footprint, lower cost, and in some other application, you can also benefit of a slower operating frequency. So those are the main reasons why people have chosen to use DSC. So there's many products now out there. I'm thinking of products like the application processor from Qualcomm, the Snapdragon series, NVIDIA Tegra, and the mobile have some product. And, there's many products now in the market. In the second part of my presentation, I'd like to show you some examples of consumer electronic application where DSC is being used today. So the first one is obviously the mobile, and this is the diagram of the MIPI Alliance that shows the cell phone subsystem. So you have the DSC encoder, which gets added in the application processor. You have your MIPI DSI connectivity. And then you have a DSC decoder that typically gets added in the DDIC chip, which is incorporated inside the display module. The main reason why people have used MIPI DSC technology in mobile has been for saving power and saving MIPI DSI lane to have a better, smaller footprint. But that's not the only application. Nowadays, people are starting to use DSC inside automotive application. When you look at the car today, the third most expensive and the third most heaviest component inside the car, after the engine and the body, is actually the cable harness. So this is very expensive inside a car. And nowadays, cars are starting to use a lot more video technology. You know, right now there are cameras everywhere inside the car. Front lane camera detection, backup cameras detection. Some people use now display for side mirrors. So there are displays everywhere. And come with the display technology, bandwidth challenges. So, you know, if you would only carry uncompressed video, you would need to increase substantially the number of cables inside car. There's various transport technology that exists today to carry video around cars, Ethernet-based, HD-based T, and others. I'm thinking of GMSL from Maxim and others. By using DSC technology at the source side, for example, application processor, GPU, or cameras, and adding the DSC decoder in the display technology, you can lower the transmission bandwidth by 3 times. And you know, the way to think about this is that you can squeeze 3 times more video stream inside the same cabling. And those benefits are extremely important to automotive car vendors. Another important consideration for automotive application is that they're very susceptible to EMI. So they don't really want to run very high frequencies. So although there are technology of transport that exists that will bring up the transfer speed from 3 to 6 to 12 gigabit per second, they're not so interested to migrate from 6 to 12 gigabit per second. And by using compression technology, it allows them to limit their reason to do that. Another good example where DSC can be used very effectively is an AR, VR, head-mounted display technology. People are now designing such product, and they're in an environment, in many cases, where it's battery operated, so they're concerned about power requirement. They also want a very cost-effective design, and it's quite common to have shared memory bus architecture where you're capturing video images that you bring to shared memory buffer. This picture are then processed by GPU or video processing algorithm while you're reading those pictures out of memory, and you bring them back inside that same memory. And finally, when it comes time to display, you're reading out those pictures to bring them to the left and right display for the glasses. By adding DSC encoding inside this architecture and storing the video images in the compressed domain, not only you save the size of the frame buffer and you reduce it by 2/3, but you're also shrinking the bandwidth on the shared memory bus. That may allow you, for example, to go from a 64 to a 32-bit memory bus. And there's many saving that you can do while doing this. Another important reason why people use DSC in AR and VR application is that because of the proximity to your eyes, people are looking to use extremely high pixel density, and also they really want to increase the frame rate to, let's say, 90, if not 120 frames per second, to have an extremely fluid experience. and very low latency. And for those reasons, of course, if you increase the frame rate in the spatial resolution, then it becomes very challenging in terms of bandwidth. So having DSC technology and work in the compressed domain for this application, I think, is a must for the future. With the advent of the DSC 1.2 version that supports YCBCR in 422 and 420, DSC technology becomes also very attractive to the digital television market. Digital television market traditionally has not been based on RGB like computer graphic. It's been based on YCBCR. And the pixel chroma sampling has been more in the 422 and 420 in the case of consumer electronic. So HDMI 2.1 will support DSC natively. So if you're looking at a DTV multimedia SoC like a set-top box chipset, for example, it becomes very interesting to add DSC encoding and decoding inside the chipset. One of the reasons is the same as I just explained for AR, VR. If the pictures are in the compressed domain inside the chipset, you save a lot of space in terms of the frame buffer. When you start to think about 8K video, of course, it's not out there yet, but I think it's coming faster than people expect. We're going to be looking at 32 megapixel per frame. It's going to take a huge amount of frame buffer to do those designs. So to keep them cost-effective, adding this DSC encode-decode pair inside multimedia SoC will become paramount. Other reason is to stay in the native compression standard. So if you have a chipset like this that wants to bring inputs from different formats, whether it's DisplayPort 1.4, HD-based, which is used nowadays in sophisticated residential DTV application, or the HDMI 2.1, well, if you're already bringing those video in a compressed domain, obviously it becomes interesting that multimedia SoC support that. Finally, you want to bring that output image to the panel. The panel for an 8K television are going to have to run at a really fast speed. And, you know, considering an 8K television will be a big panel, bringing transmission line on long distance in the back of a panel will be a big challenge. So by using compression technology and applying DSC decoding directly inside the T-Con on a chip on glass, you can actually reduce the speed of the transmission line and makes a much easier design to support. Another example is more recently, the computer that started supporting the more recent USB Type-C connection. I take, for example, the MacBook Apple computer. All support now USB Type-C. A lot of mobile cell phone also coming out with USB Type-C. It's a very elegant connector. And one of the benefits of the USB Type-C is it can carry video over this connection. Essentially, it does that by sharing the same serial link as you use for USB data, but it does it through a mode called the alt video mode. And over the alt video mode, you can transfer DisplayPort, HDMI, as well as Thunderbolt video over your USB Type-C. But there's a problem doing this. Is USB Type-C has the capability to transfer about 32 gigabit of data per second. So if I want to use a computer with two external displays, each of them supporting 4K video, I'm looking at close to 30 gigabit of data per second. So there's basically no bandwidth left in this computer to carry anything else but uncompressed video. So if you want to use your USB to establish network connection or external storage connectivity, can't too easily do that. So one solution is to use DSC. And fortunately, DSC is supported by DisplayPort, and DisplayPort over the alt video mode on USB can do that. So if you add DSC encoder in your GPU card, and this is your laptop on the left, and you carry your graphic video in a compressed domain, then you make a huge bandwidth saving that allows you to save that bandwidth for other purpose and USB. And you know, the monitors technology will eventually, because there is no monitor right now that supports DST natively inside them. So there are people right now designing USB hub technology that will use DSC, will have DSC decoder inside the hub, and will allow to decompress directly in the hub and brings a local connection of the DisplayPort to display monitor. So that's another example. As the third part of my presentation, I would like to briefly talk about how to integrate the DSC technology in your next semiconductor design. So essentially, there are two types of IP that you can purchase to do DSC design. There is the DSC encoder, and there are DSC decoder. So depending whether you're doing a source or a sync device. What you have to understand is the way that DSC works with the compression and decompression of picture images. Essentially, if you have enough horsepower inside your semiconductor to compress the entire image with a single core, you obviously do that. But if you don't have enough bandwidth because your semiconductor technology is not fast enough or the display resolution or frame rate is too high, then instead to compress the full image, you break it into two sections, and you compress the left side with what we call a vertical slice, and the right side with another processor doing another vertical slice. If that's not good enough, then you break it up in 4 pieces. So it's basically kind of unlimited, so that makes DSC entirely scalable. And in fact, you can support extremely high display resolution with fairly slow technology. And as an example, in the kiosk, in the exhibit, we're showing 4K 60 video being done with an FPGA design, which is not particularly fast technology, and that works in real time. So if I take, for example, the case of a 4K 60 application, and I have an ASIC technology that allows me to do a pixel clock at, say, about 350 megahertz, I know that in 4K 60, I have 600 megapixel per second requirement. So essentially, I will need to break up my image into 2 adjacent vertical slices in order to compress in real time my picture images. And that's what we see here. So a good DSC IP would be scalable and will allow you to instantiate more than one core in order to achieve your display requirement target in terms of spatial resolution and frame rate. Obviously, if you encode with 2 slices, you need to have a decoder that supports 2 slices. The 2 are interconnected over the transport link, and there's a negotiation that takes place, and obviously they need to know how to talk to each other. So the image needs to be rebuilt at the sync side using the same number of slices. So there are lots of possibilities to do that. So what we started working on at Hardent is to integrate our IP with various transport technology for various applications. So as an example, we have our DSC encoder technology interconnect to a cadence MIPI DSI controller. So for example, for a QHD application, which is 7 gigabit of data per second, you know, a single stream, single slice would do well. And if you're trying to run at a higher spatial resolution and frame rate, say like 4K 90 frames per second, you're looking at 24 gigabit per second, then we'd end up using two adjacent encoder interconnected to two MIPI DSI controller with a total of eight DSI lane. So there's a lot of different permutation. We've done similar architecture and design with the DisplayPort controller. And, you know, we're planning to announce additional connection with various technology like this in the future. So one consideration important also for a DSC implementation is interoperability and compatibility, especially if you make a design that will interconnect your DSC technology with third party. For example, if you do a GPU card and it's going to connect to a third party brand of a monitor, you need to make sure that there is compliance. And the DSC task group looked into this problem many months ago and came up with what we call a conformance test guideline. It's essentially a package you download from the VESA website, and it incorporates some reference pictures that you can use to test for the conformance of your design to the DSC specification. The way it does that is you have an uncompressed source picture that you're going to bring inside your DSC encoder as you test your device, and that's going to create, obviously, the compressed picture using a specific parameter set. We call this a picture parameter set, or PPS. And then you're going to decode this and reconstruct your final display images. And along the way, we calculate CRC code. And those CRC code, if you have the compliant DSC encoder and decoder, are predictable values because the DSC algorithm is bit exact. And that's a thing VESA published. And you can easily add those CRC simple circuit inside your design to make sure that you can run through those various test images and make sure about your compliance. And that's very, very important to ensure full compliance. One last word I'd like to talk about is, as we discussed earlier, VESA DSC is a scalable algorithm and can adapt itself to various technology speed, from very fast ASIC technology to slower technology, including FPGA. So not only IP like the one we designed at Hardent works well with ASIC technology, but it also works well with FPGA technology like Xilinx and Intel FPGAs. And, we've done FPGA prototyping of SoC using FPGA evaluation board like this one from Xilinx. So, in fact, if I'd like to invite you after the paper this afternoon to stop by at the exhibit, and you can get a live demonstration of DSC to appreciate the picture quality. And we have a sort of compelling way to show source image, compressed image, and show the picture quality. And you can see that FPGA technology will allow you to prototype your next semiconductor product. I leave you also with some interesting link to the VESA website and some white paper if you want to find out more. And if you have some more questions, I would be happy to receive you in the Hardent booth. I'll be there the whole afternoon, and I'll answer every of your questions. Thank you.
Thank you, Alain.